Actually a very useful lecture about ensemble models. So again, we are in classification learning theorem, and then we covered everything in the prediction model, the basic prediction classification model we want to cover. And the model we try to kind of propose, introduce today is more on top of this method because they are a ensemble approach, or like a community of classifiers. Okay, so what is ensemble? So you can think about it, it's really a committee of prediction models and trying to do the job together. And then, yeah, so there's really this crowdsourcing and all this coming from a lot of those crowdsourcing ideas. So when we talk about ensemble, the general framework is normally like this. So you have base classifiers. You can just name or index them from F1x, F2x until we normally can write like FBX. And then the second stage is how do you aggregate, how do you blend all those different base classifiers together. So this is almost all the ensemble approach follow this framework. So there's this parameter very important is how many base classifiers, and there's another important or not. There's a lot of variation is how do you blend. How do you blend the different base classifiers together? So one important properties of ensemble models is, so each of the base classifiers or base predictors, they should be diverse and very different from each other. So if they are too similar, and it really doesn't make a point at all to have multiple committees to vote together, right? Because they always have the similar votes. So this is one of the property make this type of ensemble model very appealing is, so what type of models has a lot of variations? And normally are those type of classifiers kind of vary a lot, which has high variance. High variance predictors are very good candidates for base classifiers, especially if you use bagging type of blending. All right, so this is the roadmap we're going to cover about ensemble models. So there are roughly three kinds. Bagging based, here the bag decision tree, which we covered in random forest. And the second kind is boosting. There's famous AdaBoost or gradient boost. So this is in the gradient boost. There are a few different toolbox, which is really famous in this category. Is they're all using the gradient boost idea for blending. So the bagging, the major benefits of bagging is to reduce variance. And when comparing boosting and bagging, so boosting has also the properties to reduce bias. So it's going to be clear when we touch the future slides, but just roughly have this bigger intuitions. Let's try to memorize now. It reduces bias, and also because the ensemble properties, they also reduce variance. And stacking is the third kind, which is just it's a more a meta learning, more like a framework. So the stacking just it's more about how do you blend, and boosting and bagging are more specific ways for the blending. And stacking is includes different kind of ways for the blending. All right, so what is bagging? So we already talked about bagging before. So the fundamental idea of bagging is use bootstraps of data samples in this case. So we try to just create a committee of decision trees. And then for each tree, we use a vote. Each tree casts a vote, and then together, when there's a test sample coming in, we're using majority voting from all the trees as the final decision. So this is a technique for reducing the variance for our estimated function. So basic idea we already covered, Bootstrap and we're using Bootstrap with replacement. So this is very important so for every Bootstrap sample, which means we want to learn. So in the end, if you have your base classifier is decision tree, you already decided, and you want to learn F1, F2 until FB, B different classifiers, right? How do you create B different classifiers from one training data, from one training set? And there are really limited number of choices, right? You either change the training data, or you change the training samples, right? Because to make enough differences to train diverse, different kinds of different B-based classifiers, there has to be some differences among the samples, among how do you train it. And bagging is exactly using this. It changes the training set, but it doesn't change each specific samples. And how do you change the training set? And exactly is you sample, and then by using subsamples. But I want my different base classifiers to work on the same size of training sets. And that's just to make sure the variance, it's going to be clearer later why do you want to have the same n, but just I want each of my new training set for each F1 until FB have the same size. And how do you do it? The simplest way is to bootstrap with replacement. So question about this? So it just, you sample data, then you put it back, and you sample it again until you build a set. Maybe the first set is size n. And then you start to build the second set, again, from the original training data, TR, and you create sample 1, subsample 1, bootstrap sample 1, bootstrap sample B. And each one of them has exact size as the size of the original training data, which we can use notation n. Right, so it can keep the sampling size the same as original for every repeated sampling. The sample data groups, so each of S1 until SB are independent with each other because of the sampling process. All right, okay. So then it's create S1 onto SB, and then each that bootstrapped training set, you train a model. You just train a decision tree model, and you get B models. This is B different tree models. And then you put all these decisions together. So there are various of ways to put the decisions together. The simplest is majority vote. You can also do summation. So uniform summation, which is, so each one of this is F1, F2, FB. Then I can do my final F is 1 over b summation of fi, I from 1 to b. So this is my ensemble version. So this is another way, right? So rather than doing majority, I'm just doing the mean score. I use that score as the final vector output projection. So that's the other way. All right, so when you have new data, you just feed in the first F1, F2. Okay, so you pretty clear. So if it's predict 1, 1, 2, 1, and majority vote will give you 1. So this is majority voting, right? So the decision tree, so this is the decision tree. So if you have B different decision trees, so in the end, it's kind of smooths out the decision boundaries. So when we compare this model versus this model, so let's think about bias and variance trade-off. So we always previously talked about this, right? So what's the differences in terms of bias and variance trade-off when we compare the left to the right? Right, it has a much smoother boundary. So when you have a smoother boundary, so it means the variance is actually a lot smaller on the right? So the variance, so in the end, I want to compare the variance of this summation of fi. So let's use, because it's easy to calculate the summation of, it's easy to have the analytic form of the summation function. So that's why I'm putting the summation function there. But you can also analyze, if you're using the max loading, you can analyze how the variance of this max loading grounded ensemble model. So so in fact, what we are comparing is variance of each fi versus the variance of this. Let's compare specifically for this mean case. 1 over b summation fi from 1 to b. Okay, so from the figure, intuitively, it seems variance got smaller. But how do you prove it? So this we talk about it. So actually, peculiarity of decision tree, the reason the decision tree is a high variance model, make it a very good candidate as a base classifier to be used inside bagging. And so so we're going to talk about this later. All right, so let's come back to bias and variance trade-off. So to recap, so what is bias variance trade-off? So we always use this figure, right? So this is the generalization error. So using test samples to show it has this kind of bowl shape, and the complexity of a model shouldn't be too low. The complexity of your model shouldn't be too high. So when the model is really it has high bias, like SVM, that type of model compared to your data, it's very high bias, and you're going to have higher error, but the error is mostly because of the bias. So this figure, if you still remember, we use this figure to show, because of the high bias. So if you have smaller changes in your training data, your estimator, they don't distribute too wildly apart from the mean. So this means so this is when your model has low complexity, it has smaller variance. They're all very similar. When you have smaller shift in your training data, they all still distribute very closely. However, the mean of that estimation is very far from the truth. So this is the high bias. So the majority of the error is actually from here. It's the bias, right? So this is the bias case. And on the right, when your model is super complex. When your model is super complex with smaller randomness in your training data, and it will just make the estimation distributed very wildly. And it can be here, can be there, can be in the middle, very close, but it just has a huge variation cloud. But its mean, so which means the average of all those models are closer to the truth. So if you only use one model, I mean maybe Fi, it's maybe pretty far because the randomness, right? It's pretty far. The majority of that error was coming from not from the bias, not from the mean to the center, but from the variance, just because when there's smaller shift in your training data, smaller randomness in your training data, it might give you an estimator quite different, quite far from the mean. So this means high variance, right? The decision tree model, because in the end, you trying to explore all the possible combination among features. If you think about tree, what is the tree model? So we actually talk about tree models segment the space into rectangles. And assuming smaller rectangle, those local regions have the same prediction performance. Let's just see this. If there's a small randomness in my training data, I'm assuming this blue point is not because of the sampling. This blue point is not sampled in the training data, then this whole small region will be gone, right? The blue region will be gone. And this actually means it's a very high variance model. But it's super flexible, right? If assuming you have a few blue points in here, I don't have blue color, but I'm trying to show you, it has the ability to just have a bounding box to show that should be the blue class, right? So the decision tree is extremely flexible model. Its decision is super nonlinear. It captures interaction among features, right? If you remember, it's a tree model. From the root to the leaf, it's a lot of decisions. In the end, it's an interaction from the root, from each level, each node, it's a feature. And then in the end, each path representing a very complicated interaction among many features. So it's extremely nonlinear and flexible model if you have a very deep tree. So deep tree or wide deep trees, it's very, so if you have a full length of trees, it's a super flexible model. All right, so let's come back to this figure. So the tree, if you have the full tree or the big trees have very high variance. So then the issue here is to reduce the bias, right? Reduce the variance. Yeah. All right. So now let's see. So you have multiple classifiers, and each one of them corresponding to a estimation. Because think about the Bootstrap samples. What we are doing in the Bootstrap samples. If you remember, we bootstrap S1, S2 onto SB. In fact, we are creating randomness of my training data, right? And that create a lot of variations of the estimation of the different estimators, and by considering the randomness in my training data. Because this is a high variance model, it's very flexible, right? And then its mean is supposed to be closer to the truth. Okay, now let's just use the mean. And that's exactly the point of bootstrapping, and then together taking a decision from a committee of decisions. So we average all the F, and then the average of all those F estimations, Fi, they are more closer. So this should be flipped. So this is the truth, and this is the estimator. So we average complex models to reduce variance, and then bootstrapping is to creating those randomness inside the your training data. So now let's see, how do you prove this? What is the variance of multiple random variables, right? That's the first equation we should look. So this is the general equation. When you have a random variable x and a random variable y, the variance of ax plus by, it follows this, it's an axiom. It's equivalent to a quadratic variance x plus b quadratic variance y, and then times 2ab covariance x and y. So in our case, who is x, who is y? So it's each estimator from different bootstrap samples, right? What I care is that variance of this bagging decision, which I just use a mean to represent it, variance of 1 over b summation of all the fi, you can actually derive this, and assuming this, it's actually not directly can be converted here. So in fact, I'm assuming all the f1 onto fb, their covariance equal to 0. Otherwise, there's no way I derive this. So when the covariance of fi and fj, all the possible pairwise covariance of each trees is 0. And I can derive, so because you have total of b, I from 1 to b, right? And I'm assuming each one of them has the same variance. So this actually can be approximated if the training data have the same size. So S1 size n, S2 size n onto SB size n. They are all the same size, and I actually can assume it's almost guaranteed the variance of each Fi is the same. And then this equivalent to, because they're total B, right? Variance, maybe let me write down here. So variance of F hat, which is the back version, they are 1 over B, summation of I from 1 to B, Fi hat, okay? And if 1, so that's just so 1 for all the I and j, covariance of Fi and Fj is 0, I can get the above is 1 over B quadratic summation of variance of each. And then, because of the sample size S1 onto SB, the sample size are all equals to each other, because, and then because we know S1 onto Sn, they're all, can that work? Okay. So S1 equals to S2 onto SB, they equivalent to each other. That's why I can roughly assume variance are approximately similar. The variance of Fi equals to variance of Fj. And because of all those, and then this gives me what? The variance of F is 1 over B variance of each. Which is this solution. So the variance of the back tree is 1 over b of each of the tree, assuming you're training the model the same way, and also each subset has the same size. And also, the different trees are not correlated with each other at all. They're totally, the covariance among each trees, all the tree to other trees are 0. And this is 1 over b variance f. So this sounds, why do I need to derive this, right? And it will be very clear later. So, okay, question about this. There's a lot of assumption here. I'm assuming all the trees are not correlated to each other. Their prediction are not correlated to each other. All right. Yeah, so, okay, so now let me show you an example which shows the previous assumption doesn't hold. In fact, if you just do Bootstrap and then learning decision tree on top, the learned trees are very correlated with each other. So let's use an extreme example, a very extreme simulated data to show you what is the behavior. So let's just assume a super small training data with only 30 examples, or maybe 300. So there are two classes, class and minus, or maybe let's just do 0. So y belongs to 0 and 1. And you can just do normal simulation to sample 5 features and just normal distribute it. And you can also control the pairwise correlation among the features are super high, which in this case you can just control they are 0.95, which means this is almost equivalent to the homework 2 you did about ridge regression. And if you remember, so there's x1, all the other features are very, very correlated with x1. Actually, in the ridge regression, is ridge regression or the other one? Yeah, in the ridge regression, maybe it's totally random, if I remember. There's another, yeah, so it's, in the end, you're simulating data to check the performance of your method, right? This is a very good sanity checker. So, okay, so now I'm generating x1, x2 onto x5. And they are almost the same feature. Each feature are very correlated with each other. And when x1 is bigger, and the other feature are also really, really large because the positive correlation, right? So x1, when x1 is large, x2, x3, x4, up to x5, they're all very large, which in the end means this data, it essentially has only one feature. But when you, in your observation matrix, these are 5 features. And then you just using a rule to generate y. So this is your generating training data to see if your decision tree can learn a good classifier, right? So it's a super easy rule. It just, if x is smaller than 0.5, x1 is smaller than 0.5 will be more likely to be class 0, y equal to 0. And then, and then if x1 larger than 0.5, and then, it's exactly that. When it's larger than 0.5, and it's mostly 1. When smaller than 0.5, it's mostly 0. So it's a super easy classification, actually. x1, and then there's a 0.5 there. So on the left is 0 class, and on the right is 1 class. And of course, this probability is to generate some there's some kind of noisiness there, right? It's not fully deterministic. So you observe samples on the right, something like here, and sample here, but you still have a little bit of noise sample like class, and a little bit noise sample like this. So this is your observed sample. So the majority, if x1 larger than 0.5, it's class 1. Majority, when x1 smaller than 0.5, it's class 0. Okay, so why do I even care about this data? And then you use this data to learn a decision tree, to see if it can learn a perfect decision tree or a good decision tree or not, because this is the simplest ever data. And also it's the simplest ever decision rule, right? There's only one rule necessary. Let's see if your decision tree can learn it. Okay, so now you learn 500 trees. The problem, and in fact, what you're going to learn are many different kinds of trees. They look very, very different from each other because you random sample your training data, right? And because there's high correlation from X1 or X2 or X3 or X5, it's very difficult when you have just some randomness in your training data. It's very difficult for your classifier to pick which feature is the top feature, and then the next feature, and then the third feature. When should I stop? And what's the depth? When should I stop? When should I prune the tree? How should I prune the tree? So this creates a lot of different kinds of trees. They look quite different from each other. But because of this data, in fact, the trees are very, very similar predictions. So even though on the surface, the model looks very different from each other, but their decisions are almost similar. And whenever there's a fixed X or X1 onto X5, a certain test samples, the prediction of each F1, F2, so like F1X, F2X onto FBX, it's almost the same. So this actually tells you, even though the model looks very different from each other, but in fact, the decision is highly correlated with each other using the bagging trees, in the bagging strategies. So let's come back to see what, I'm going to clean this up. What matters is what? What matters is the decision. It's a decision, right? I'm trying to reduce the variance of the decision in this case. Even though the models are quite diverse, but the decisions are highly correlated, and there's no way a bagging strategy can work well on this data, on this type of so correlated data. So, and you can also tell, it really doesn't matter how many treat B when you increase the B. So roughly when B equals to 30, and it just, the performance stops to improve at all. And in the end, the issue is the decision trees on the Bootstrap sample sets, it's highly correlated with each other. And they make very similar decisions. Okay, so this means what? When we do this variance of 1 over B summation of Fi, and we actually cannot make that assumption, covariance between Fi and Fj equal to 0. And that makes what? The whole variance of this summation, this ensemble, this bagging of trees, is not necessarily got reduced if the covariance is too big compared to the just each of individual trees. So this is the final conclusion, a summary conclusion I want to see about bagging decision trees. And then the whole reason is it's very correlated. It's only slightly increased the model complexities. And so because bagging trees are so correlated, then people come out with a strategy called random forest. The whole idea of a random forest to reduce the correlation among trees, which trying to reduce this item in this variance calculation in the end is not straightforward summation. This correlation among models is truly important. And it's trying to reduce the correlation among different models. Okay, so random forest. What is random forest? Random forests use decorrelated trees. That's the fundamental idea. But in fact, the whole procedure, the pipeline, is almost the same as bagging. The only difference is, so I'm still doing Bootstrap sample of my training data to get S1 onto SB, and each one of them have the same size as the original training data. And different now is when I'm trying to do the splitting, rather than using consider all the P features, I'm trying to get a random subset of features, like M features out of the P. I only pick splitting features from that M subset. For each split, you perform a feature subsampling, and then you pick the best among that M. So in the end, if you think about it, so this level of Bootstrap adding randomness of training data, and this level adding randomness of features. All right. So same thing as before, you grow B different trees, and specifically the specific random forest always is a binary tree. So I did not cover there's the variation of trees last time. So in fact, there are a lot of different kinds of basic decision trees. ID3, C4.5, CART, and random forest, the specific random forest people normally use is built on top of the CART decision tree based learning. So I have some extra slides in the previous decision tree lecture. Feel free to check out. So what makes the differences of ID3 versus C4.5 versus CART? So there are actually quite some differences what they make. And also the specific random forest, the splitting measure it used is Gini impurity measure. It's not information gain. Information gain was mostly used in C4.5 type of decision tree learners. But they're actually very similar to each other. If you remember, they all have this kind of bell shape. I mean, the more uniform the distribution, the higher the measure, the lower on each side is what you prefer. So the pure node is what you prefer. All right, so you grow B different trees, and at each split, there's only M random subset of your feature are considered. So then you can, again, doing majority voting or doing mean prediction, and it's all can be, it's all supported in the package. All right, so more concretely, so for former tree, one given P dimension, you pick M of the dimension. You split only according to those M dimension, and it's not you're not going to consider the P minus M dimension at all at that split. And repeat this 1 and 2 procedure for every split. So which means for every split, you pick a different subset of M features. Question about this? Random first? Sure.
Can you repeat some of the features?
Yes, you actually can. So this, then the very natural question is, so what M? How many M should I use, right? So this, the author actually did a lot of experiments trying to see, give guidance of what M to pick. So it normally has this kind of plateau. So in the beginning, it gives good performance, and then so in here, good performance means the correlation. So the correlation, the smaller of the M, the lower the correlation among trees. So you can see the y-axis is the average correlation among trees, which is extremely small. It's about 0.06, and then when you have a lot of M, so it kind of increases correlation. and then you normally stop at a certain number, which it's in the next slide, the author has a guidance about what M to pick. So there's a good balance of the number of trees, because the more the tree, the more computational cost, right? We cannot just see, wow, if the bigger the B, the better. Let me just grow many trees, right? Or many base learners. And there's always the cost of learning cost, memory cost, training cost, and test cost, right? You also need to consider everything together. So, but the correlation, we should actually keep that number here, this rho. So if you still remember what is correlation, so we actually introduced the correlation equations in feature selection lecture. And we know 0.06 is extremely small correlation number. So correlation is from, so upper bounded by 1. If it's 1, it's fully positive correlated. And when it's close to 0, it almost means there's no correlation. And this has a slightly correlation, but very close to 0. And then why do I even care, right? It will be really clear why that rho number is important. So now let's first see, so what's the M values? In fact, if you think about it, when M equals to P, this model is exactly baggy. And normally for regression tasks, people recommend, the author actually did a lot of theoretical analysis to recommend log P or P over 3 for regression choice. And also for classification is square P. So if you want to understand why, actually feel free to read original random forest papers. It's a very solid theorem-grounded work. So even though you can think about, wow, so it's so simple, right? I bootstrap my training set, I'm growing B trees, and then I'm putting this together. So intuitive and easy, but there's a reason why you pick M features and how do this influence. The paper itself has a really nice analysis about this choice. Okay, so now let's come back to this original motivation to do decorrelated trees, right? So why correlated trees are not ideal? So I give you a simple explanation from this variance of AX plus BY, but more concretely, so what is the concrete formula for the decision tree of a random forest? So let's assume each tree has a variance sigma squared. If the trees are independently identically distributed, then the average variance is sigma squared over B. I actually proved it, right? I used this to, it's very easy to prove, is 1 over B sigma squared. Because correlation are 0, and then the scalar becomes a square because every share the same scalar, 1 over B, and then you have a scalar 1 over B quadratic, and then each one of the base classifier, the variance is sigma squared. You have a total of B such base classifier. This gives you B sigma squared, and then the final outcome is 1 over B sigma squared. Question about this? It's actually very easy to prove this. Yeah, just from the basic sum of variance equations. All right, so yeah, I should remove this animation, but okay, now let's see if there's a correlation, there are correlation among trees, what is the variance equation? And this actually is the equation of the final joint model if there's a correlation. Of course, you can tell, actually, I'm assuming each pairwise correlation is the same row, but there can be more settled representation, like row 1, row 2, row ij. But let's just assume all the possible row ij means the correlation among fi and fj. They all equals to row. And then this is the variance of the f. If you're assuming f equals to 1 over b, a summation of fxi. And this looks pretty weird. So why do I write like this, right? It's actually very easy to see. So when you have more and more b, and this denominator becomes super large, which makes this portion just not matter at all. And then the whole variance of the model is controlled by rho and sigma square. So which means you really want to decrease the rho and to make the model, to make a smaller variance. Because when rho equals to 1, and this is exactly like the base classifier, right? Your base classifier has sigma square, and then when you have b, different classifier, their variance still sigma square. And then think about what is the whole bagging or random forest. There's no benefit it brings me at all. So that's why, and this rho, it's important. When I have 0 point like close to 0, this is a huge improvement over the base classifier decision tree. Okay, question about this? All right, sure.
Is there still any like limit for b? Like we shouldn't increase it more than a specified limit?
Yeah, so good question. So the question is, if the bigger the b, the better. Why not just pick a super large b, right? It's almost that. How do you pick the right b? Yes. So like I just previously mentioned, here it's only about variance, right? But when you have bigger b, there's some other cost. There are actually a lot of cost if you think about it. First of all, data cost. I mean, you sample and then the hard drive, it's b times whatever you have, right? So let's just see RAM cost is times b. Then there's also training cost, right? We always do calculation about what's the training cost for each base classifier. And then this also times b because you do b of those. And maybe training like time, it's fine because you can do, you don't care how fast you train this. But if during the testing, and especially k-nearest neighbor type, right, when you have b such models, and this is actually b times of the inference cost too, right? It's really a balance you have to pick. And you can't have too many b. Of course, if you go Google or Facebook or they just go to the distributed cloud and use as many as b servers that you wish. Those are the good situations. Yeah, but we normally don't. Okay, yeah. But you can tell, I mean, this time of ensemble classifier is extremely parallelizable. And this is actually a benefit if you think about it. Extremely parallelizable. Yeah. More question about this? All right, so let's go to boosting. So so in the end, we reduce the pairwise tree correlation, and then because the row gets smaller, so that's why the total variance of my random forest model got reduced. It's very clear from that equation. Okay, so before I talk about boosting, I want to talk about stacking. So to talk about stacking, there's a really classic competition which got an ensemble into people's eyes is Netflix prize. So I think you maybe all know what is Netflix competition, which is this user movie reading competition. So there's a lot of training data. It's about 100 million data. And then you're trying to predict for a new user, I mean, are their ratings. And this is a 1 million prize for 10%. So whoever achieved 10% improvement over the Netflix baseline, you're going to get a 1 million prize. So people in the leaderboard just try really, really hard. And who is the first, right? So it's not who is the best. I mean, here is who's the first to reach that 10% improvement. It's a very funny, actually, funny story. So this group called, it's actually a matrix decomposition based idea. I think it's from Intel. It's called Bowker's Pragmatic Chaos. And then the second team is ensemble based. And the first team and second team actually got exactly the similar performance. But the first team is 20 minutes earlier. So the first team got a 1 million prize. But this still tells you how powerful is the ensemble models. In fact, the ensemble models here are just divers of kind of predictors. And it's not complicated at all. It's a complicated model, but it's very heuristic driven. The first group, it actually has a lot of, it's this specific task grounded approach. It's a matrix decomposition based approach. You should check out the first method, but second method is like a pipeline. And if you check out the recent Kaggle competitions, and in fact, you don't even need to understand the data much. You just run an ensemble of a lot of algorithms. And normally, and as long as you don't do stupid mistakes in data processing, that type of data processing mistakes happen a lot. And you formulate correctly to using each of the base classifiers, you have a reasonable blender to put them together. It always gives you really solid, good results. All right, so what is stacking? So we told you about ensemble, about random forest and bagging, and owing to blending approach we told you is majority voting or the mean, right? 1/b, summation of each fi. But think about why do you need to limit yourself into those heuristic-driven max function and the mean function, right? If you think about what we use in the majority voting is max function. And what I use in the 1/b is the mean function. You really don't need to limit yourself to that type of fixed function. Yeah, mean or max or some other type, uniform summation, or how about just train a second level blender, second level classifier, or second level additive summation with the weights. And you try to use the second level to get the best weights to do the combination of each base classifiers. And this is normally called a meta learner, or we can see that they're blenders. And then to perform the final prediction. So this, everything here, so if you treat a meta learner, so whatever meta learner, it all follows this, you can call them a stacking model. Because it's stacking a second meta level classifier on top of the base classifiers. So question about this? It's extremely easy. The prediction from different F1, F2 until Fi. F1, I should use B here, like FB, and then you have a different level. Let's see the G function. In the end, you're learning a new function G to combine F1 to FB. Sure.
Is this here kind of a linear function only, or it can be any?
Can be a lot. There are many different kinds. Yeah. The most intuitive is a linear function, right? And you really just learn the weights of each, the weights on top of F1, on the weights on top of F2, the weights on top of FB, right? But you're really not limited to just linear function. It's just another classifier you can think about.
Because before we were just taking the mean or the max.
Exactly. So what we did in the bagging, and it's either mean or either max. They're just fully heuristic driven, right? So maybe some base classifier is more important than some other. You don't want to just treat them the same, right? So this gives you another level of flexibility to consider the different base classifier in through a different combination. All right, so there are many kinds. Then in the end, for your base classifier, you need to think about accuracy and this diversity, right? It needs to be not too strong bias, not too similar to each other. And how do you create F1 onto FB, right? You sample the training data, or you sample the feature, or you use different models. You just use different method. SVM, k-nearest neighbor, whatever, things seem making sense. They can all be a candidate in this as a base learning. And then how do you put them together? So what I said, it's a supervised way, right? But you can also use unsupervised way. Like we said, majority voting or weighted mean, there's even k-means based, which we're going to cover later. So in the next about unsupervised method. How do you train it? So you normally need to split your training data now into two sets. The first subset of training data is used to train different base classifiers. So F1, F2, onto FB. And then on the second training subset, some people call that validation data, or So you actually on top of that subset, you're training the G. So this is the output from F1. You're using all the output from F1 to FB as features. And then you're training a second level G function using the F1, F2 onto FB. And so in the end, you are using a different, a left out to train the G function versus the Y. And there's a loss function here. Again, the same procedure, right? Loss function Y versus the G, and then you can use many different strategies to train the G. Okay, but pretty critical. There should be differences among subset 1 and subset 2. The one used to train the base learner and the one used to train the matter learner. All right, okay, so questions about this? Sure.
Generally, I mean, let's say all these functions are only decision trees, and in another case there are like decision tree, SVM, KNN, and like different ones. So does the variance matter? I mean, in the first case there will be more variances compared to the later case or something.
Yeah, so very good question. So the question is, if F1 onto FB, they are bootstrapped different decision trees. And this is the first case. The second case is I don't change my training data, I change my training algorithm. So I train SVM, k-nearest neighbor, decision trees, or maybe logistic regression we learned, 9 days. These are also variations, right? And then you train a different level of G function. So which one is more preferred in this case? So I think, in fact, for the stacking kind of model, I think changing the algorithm is more preferred, because there's a much better strategy when you F1 onto FB, they are all decision trees. There's a much better strategy. You don't need to do so they're much smarter stacking. If F1 or F onto FB are all decision trees, the much smarter stacking approach is actually called boosting. It's exactly after the stacking I want to talk about it. It's next. All right, so now let's talk about boosting. Boosting, you can think about it just a specific kind stacking approach, but it's a very smart kind of more inclined. It's designed very specifically to, it fits decision tree very nicely. Yeah. So yeah, I copied these examples from somewhere. Like let's see if this make a point. So you try to classify the real apples versus plastic apples, and then you really try to make super simple. You try to learn super simple decision rules as base learners. In this case, my base learners are mostly very super decision rules. So maybe just one layer of decision rules. Some people actually call that decision stump, right? Will be one layer or two layers or maybe just a few layers. So if I have, let's just write them as shallow decision tree. What's the issue of shallow decision tree? What's the property of shallow decision tree? Bias and variance. So the shallow decision tree has the property of
High bias.
yes, high bias. All right. So then you sequentially train a base classifier to correct the mistake of previous rules. So now we don't do bootstrap of my training data. I just work on the same training data, but I'm training a sequence of base classifiers. So I don't, like before, I'm doing parallel type of parallel type of decision tree training, right? It's just one tree, Fi versus Fj, they really don't dependent on each other at all. It's completely independent. But now I do this procedure sequentially. And every step I focus on hard examples, and I'm giving higher weight to better decision rules that I learned. Okay, so I have training data, and then I try to learn using the Olin thresholding function. Olin thresholding. So I can't even have this type of linear classification because I only allow thresholding operations, which is what? Thresholding operation on this figure is either this or either this, right? There are only two kinds of rules. Either thresholding the color x1 or thresholding the weight x2. So this is the only two type of rules I'm allowing, which is super high bias, right? How can I figure out a best decision tree or decision functions using only these two kinds, either thresholding on the x1 or thresholding on the x2? All right, so first simple rules based on loss function, right? This is almost the best you can. Almost the best, to minimize the training loss, because it's only allowed to do thresholding. So this is the best you can, but it makes mistakes on here, makes mistakes on there. So now I focus on this and that. Okay, so now I try to relearn, but I emphasize this two should not make mistakes. And now this two doesn't make mistakes anymore. Okay, so this is the second rule I learned. I only allow either this thresholding or this thresholding. Okay, this is all follows what I allow, right? But it's super high bias based learner. All right, now I'm making mistakes on this and that. I emphasize next time, please correct this too. Now I'm learning further. Yeah, so this got predicted correctly, but this actually not. But this gets predicted correctly. This is on my x3. All right, so then there's a huge amount of examples not predicted correctly from x3, right? Now I'm learning x4. I want to predict all of those correctly. This is x4. So in the end, and there's all this x1, 2, 3, 4. They're all super simple decision rule. And then the final classifier is a combination of the four by treating different decision rules with different weights. And this is what you get from a boost. So what you allow in the base learner, it's very, very rigid. It's only allowed to threshold this direction or threshold in that direction. But the combination can give you very flexible decision boundaries. So how do you do this? So first, you have a weight on each samples. Sorry, I'm a little slow. Let me quickly go over that, but the figure tells you almost everything. You learn the best base learner by optimizing the current laws. And then this is the decision, this is actually the definition of that loss. It has the weight from each example. Each example is treated differently in the loss calculation. And this is a very key point about this loss function. And also, you are assigning weights for each base learner. So this is an additive summation of different base learner, but that weight is actually learned. It's controlled by this error you just get from the specific base learner you just learned. And the final, and also you are updating the weights on each example based on your current predictor. If it's made a wrong prediction, you're going to give the really high weights on those examples got predicted wrongly. And the final classifiers is this summation of alpha t times all the base learner. So there's actually a lot of theorem behind why the choices of the weights of examples, why the choices of the weights of classifiers, which I have a lot of extra slides if you want to read those. All right, so sorry, it's kind of quick. So there's only one thing I want to talk about is boosting versus bagging. So similar to the bagging, boosting reduces the variance because the ensemble. And unlike bagging, boosting fit the tree to the entire data and adaptively weight examples. And boosting trying to do better at each iteration. It's trying to do better at each iteration. In fact, so even though each base learner has high bias, but your blended learner, it's a summation of alpha t times all the base learner, right? That blending, in fact, reduces the bias because it's trying to be more and more complicated. So this blending is more, so each base learner covers something your previous learner, everything touches so far, not covered. It makes the whole model space slightly grow at each iteration. All right, so I don't have time for XGBoost. So XGBoost, in fact, so